Good morning, PreCalc. Today we are going to do a double lesson on sections 3.7 and 3.8, and it actually really follows along nicely with our 3.6 reciprocal functions. You're going to see how it ties right into that. So today's lesson is all about rational functions. Just like fractions can be proper, improper, you can have proper, improper, rational functions. So I've decided to combine them and just do one lesson overall on rational functions in general. So what is a rational function? There's a definition box on page 151 in our textbook. I essentially like to call it an ugly fraction because it is not just a simple fraction. There is a lot going on in both the top and the bottom, but essentially it's just a big fraction. So here are a couple classic examples. See how you have a lot going on up top, a lot going on the bottom, a lot going on up top, a lot going on the bottom, but essentially every time it's just a big ugly fraction. Now, I should say that the denominator can never equal 0 because that would make your fraction undefined. So we should keep that in mind. We're actually going to use that as we work because that will help us find our domain, just like it did with reciprocal functions before. All right, so what are we going to do with these big ugly fractions? Well, if you're wondering how this ties into our last lesson, sometimes a rational function has a 1 in the numerator. If it does, it literally is a reciprocal function, just like we did in section 3.6. But if the numerator has something other than just a 1 in it, then all of a sudden you do have some extra steps that you're going to need to do in addition to our last lesson. But before we go into the extra steps, let's just do a quick review of what we should have taken away from our reciprocal function lesson. First point, when you have a reciprocal function, again, that's just a 1 over bunch of stuff in the denominator. You will first of all set your denominator equal to 0 to see what values are not included in the domain. And for reciprocal functions, whatever you find to not be included in the domain is automatically where you have your vertical asymptotes. Okay, that's going to just change a tiny bit this lesson as we add in the concept of holes in your function. Literally like a hole, like a circle hole in your function. All right. Reciprocal functions are always bottom heavy, we learned last lesson, which means there was a higher degree in the bottom rather than the top. So because they're bottom heavy, we always found the horizontal asymptote at y equals 0. Now that our functions are a little more complex, we might find that sometimes there's no horizontal asymptote. Sometimes it is at y equals 0, or sometimes it's going to be somewhere else, and we will discover that as well. Finally, when we sketched our reciprocal function, I asked you to please include your vertical asymptote, your horizontal asymptote, which was the the x-axis, your y-intercept if possible, and any extra needed points in the regions in between to get a good sketch. All right, so that was our plan for a reciprocal function, but we're moving on to the broader topic of rational functions today. So you can follow the steps above if there's a 1. If there's anything other than 1, you're going to need to follow the steps I'm about to introduce right now, which are very similar to the other ones. The steps I'm about to show you work for all rational functions, even reciprocal. So you could just always follow these steps. I was just trying to give you a little shorter one if you know you have a 1 in the denominator, because that does happen sometimes. All right, there are 6 total steps. Let's start right off at the top. All right, step number 1. This will always be your first step, and that is to simplify your rational function. In order to simplify, I want you to factor the top and the bottom, see if any factors cross off. Step number 2, check for domain exclusions. Just like before, you will set the denominator equal to 0 to see what values are not included in the domain. Now, the only change here is at the domain exclusion, there could be a hole or a vertical asymptote. And we know a vertical asymptote is just a vertical line that the graph is going to get really, really close to but not cross. So it's going to show you that behavior of the graph. A hole is exactly what it sounds like. If there is a hole, you might be drawing your graph and there's literally a hole at that point. So I should really erase the very inside if I can do that. I think it's going to erase the whole line. All right, wait, let me try this one more time. If there's a hole, you have a graph and then all of a sudden there's a hole, you have to pick up your pencil and keep drawing. So you actually don't even have a continuous function at that point, as you don't with a vertical asymptote either. Now, to find out if it's a hole or a vertical asymptote, It's a whole if the factors match in the top and the bottom. It's a vertical asymptote if they don't. So let's just take a quick hypothetical example so you can see what I mean. Sometimes it's hard to just hear all the words and make it work with numbers. Let's just say you had as your function x plus 2 over the quantity of, we'll do x squared. We want to make it something that's factorable. So let's do like 6x plus 8. All right, you go to your very first step and you say, my first step is to simplify by factoring. Well, you're not going to be able to factor the top. We'll just leave that x plus 2. But you can definitely factor the bottom into 2 parentheses. Can anybody think of 2 things that add to 6 and multiply to 8? Multiply to 8, add to 6. 4 and 2. X plus 4, x plus 2. Look at what's happening here. I see a direct match in the top and bottom. So I've now simplified my function to y equals 1 over x plus 4. Now, let's talk about my domain exclusions. When I set this initial denominator equal to 0, I found that in the domain, there was not a -4 and there was not a -2. If I wrote that in interval notation, it'd be really long. It would be parenthesis, -infinity to -4, close the parenthesis. U, -4 to -2, close the parenthesis. -2 to infinity, parenthesis. That would be my domain exclusions. Now, there is a whole at x equals -2. There is a vertical asymptote at x equals -4. Now, I'd like to know exactly where this hole is. So if I plug in a -2 for this x down here, imagine this said -2, that would be 1/2. That means the hole actually occurs at -2, 1/2. So at that, I don't even want to say at that point, at that location on the graph, I would draw an open circle to show I have a hole there. So that's the big thing that we just experienced. Instead of just vertical asymptotes, now there can be holes or vertical asymptotes. All right, let's look at our next one. So we have already gone through the first 2 steps. We've simplified. We found our domain exclusions, which included our holes or vertical asymptotes. Third step, find your horizontal asymptote. Now, up to this point, you have only known that if it's bottom heavy, there's a horizontal asymptote at y equals 0. We have 2 other things that can happen. Your function could be top heavy. If it's top heavy, which means the degree is bigger on the top, there is no horizontal asymptote. If it is balanced, that means your horizontal asymptote exists at the equation y equals whatever the leading coefficient of the top is over whatever the leading coefficient of the bottom is. And I'll show that. I have an example right below these rules, but I just wanted to go over the rules with you first. I mentioned this last notes, but just a quick reminder, a graph can cross a horizontal asymptote. Horizontal asymptotes just teach you about the tails of your graph, but vertical asymptotes can actually never be crossed. Page 153 in our text explains that as well. Oblique or slant asymptotes can be crossed, but vertical asymptotes are no cross zone. Finally, we know that reciprocal functions were always bottom heavy, so that's why we always knew the horizontal asymptote was at y equals 0. Now we have to keep in mind top heavy, balanced, or bottom heavy. So let me get to this picture. I really feel like this is a great illustration for horizontal asymptotes. It gives you 3 different examples in this picture. Now, in the first example, you will notice that it's top heavy. See how the degree of 3 is larger than the degree of 2, making it top heavy. As soon as it's top heavy, you can just say none or no horizontal asymptote. No, HA. All right, nope, I'm going to jump down to the third example. We did A, let's do C. In the third example, see how it's bottom heavy. The 5 is bigger than the 1. In our reciprocal function, this has always been the case, so the answer is just y equals 0. Now, the middle one is the one I actually think is the most complicated. The middle one is when the degree is perfectly balanced. See how the degree is 3 and the degree is 3. When that's the case, whatever the leading coefficient of the top is, in this case it's -1, over whatever the leading coefficient of the bottom is. In this case, it's 3. Becomes your equation, y equals -1 over 3. That's where your horizontal asymptote exists. So on a graph, you would actually have to go to -1/3. So it'd be like here, really close, and sketch in your horizontal asymptote right there, as opposed to being right on the x-axis or not at all. All right, step 3, we only have 3 more steps to go. You're doing great so far. Step 4 is highly related to the horizontal asymptote step. I usually kind of do these at the same time. This is an oblique or slant asymptote. And an oblique or slant asymptote only occurs if your function is top heavy by 1 degree more than the bottom. So only in top heavy if the degree on top is 1 more than the degree on the bottom. So for example, if your top was something x to the 4th over something x to the 3rd, a slant asymptote exists there. If your function was x to the 3rd over something with an x squared as the leading, 1 degree top heavy, there would be an oblique asymptote there. We're going to get into how to do those when we get to our example section. But if an oblique asymptote exists, which is kind of a rare occurrence, I mean, that's only when it's perfectly 1 degree difference and it's heavier on the top, you will do long division to find the equation of the slant asymptote. The good news is you won't have to worry about the remainder. You'll just do the long division part and get the quotient before the remainder, and that will be your equation. Like I said, we'll get to that in the examples. But if it's not top heavy by 1 degree, you can simply say no oblique asymptote and move on. So that's not going to happen too often, but you do want to be prepared for when it does. All right, final 2 steps. First one, find both intercepts. To find the y-intercept, that's where x equals 0. Turn all x's into 0 and evaluate, just like we did before. To find the x-intercept, I actually find this one kind of interesting because you turn the y equal to 0, which would be like the whole left side of the equation, essentially. But it's only where the numerator equals 0 because we already said the denominator can't equal 0, and that's how we find vertical asymptotes. So when you set the function equal to 0, you can really just set the numerator to equal 0 and go for it, and you'll find the x-intercept that way. Just a little shortcut because you won't have to worry about the bottom of the function at all. All right, let's keep cruising along here. Your final step is to sketch it. When you sketch it, use all the information above. So the vertical asymptotes, the horizontal asymptotes. Let's kind of peek through as we're talking about them. Use all the information, which means you already simplified. You did the domain to find the holes or vertical asymptotes. You found the horizontal asymptote. You found the oblique asymptote. You found y and x intercept or intercepts, depending on how many you find. Then you find a few extra points as needed to see where your curves occur, and you're done. Quite the process. Glad you have this typed up, and I'm glad hopefully you're jotting this down in your notes so you have it written down too. All right, here's the process in a nutshell. I kind of just wrote it as one line here. You simplify, you find the domain, vertical asymptotes, holes, horizontal asymptotes, oblique asymptotes, intercepts, extra points as needed, sketch, and then you're probably going to want to check it on your calculator because it'll make you feel really good when it matches your sketch. Big process. Learn it for the quiz. On the midterm, you can write the whole process down on your note card and bring it with you into the midterm. The best way to get good at this is to practice it. I'm going to do 4 examples with you right now, which I think you're going to find really helpful because we're going to go over all those steps each time so you can really see how they work. And then for homework, I'm going to have you do 10 questions, which kind of just give me an idea that you can follow certain parts of the process. You can follow the directions in the textbook. Then you're going to do it with 3 graphs. You're going to go through this whole process on your own. Don't even use the given directions. Just go right to the whole process, which is simplify, domain, vertical asymptotes, holes, horizontal asymptotes, oblique, intercepts, extra points as needed, sketch, check on your calculator. I listed a whole bunch of areas you could go for extra problems in the textbook if you need extra problems in this section to kind of like really get good at going through the process. But let's jump on our whiteboard and start working through some of these examples so we can make some headway. And here is our first example. You might want to pause the video and just make yourself a list of all the info you're going to need. It'll really keep you organized. our first step is to always simplify, and that's by trying to factor the top and bottom. The bottom will factor if we can think of something that adds to -3 and multiplies to 2. Must be 2 negatives. So the top will just stay x plus 2. But the bottom must be x minus 2 and x minus 1 because that adds to -3 multiplies to 2. Nothing crosses off, which means I do not have any holes I can tell right away. All right, but let's go ahead and find our domain. So domain says that we set the denominator equal to 0. So I already factored it. If I set this equal to 0, I'll get 2. And if I set this equal to 0, I'll get 1. Those are the only two values excluded in my domain. So x cannot equal 1 or 2. Now, if I write that in interval notation, I'm going to go from -infinity up to 1. Then I'm going to go from 1 to 2. And I'm running out of room here, but then I'm going to go from 2 to infinity. There's my domain. Now, vertical asymptotes occur at both of these spots since there was no holes. Vertical asymptote at x equals 2 and at x equals 1. All right, next step, we want to know if there is a horizontal asymptote. So is it bottom heavy, top heavy, or balanced? The degree of 2 is bigger in the denominator, so this is bottom heavy, just like our reciprocal function. Whenever it's bottom heavy, our rules tell us there will be a horizontal asymptote at y equals 0. If it's bottom heavy, I know there can't be an oblique because oblique only occur when you're top heavy by 1, so there's no oblique asymptote. All right, next step is to find the y-intercept. I find the y-intercept by turning all of my x's into zeros. I can do this in either version. I'm going to just do it in this one. I think it might be easier for me to see. I'm going to turn all of my x's into zeros. So that would just make the top 2. This would be 0 minus, if that's 0, plus 2. So that would be 2 over 2. There is a y-intercept at 1. So I'm going to write that as 0, 1. Let's find the x-intercept next. To find the x-intercept, I simply set the function equal to 0. But remember I said you can really just set the top equal to 0 because we already dealt with setting the bottom equal to 0. When I solve this, I get x equals -2. So there's an x-intercept at -2, 0. Now, it is too soon for me to know what extra points I need. So I'm going to graph it first, and that will determine what extra points I need. Let's start with our vertical asymptotes at x equals 2. Went ahead and counted this graph off by 2 again because I thought it might be easier for you to see. So first vertical asymptote at x equals 2. All right, next vertical asymptote, at x equals 1. This is so close by. Kind of wish I had counted by more than 2 now that I'm looking at this, but let's stick with it here. X equals 1, x equals 2. There are no holes to worry about. There is a horizontal asymptote right on the x-axis. So I did dash that even though it's a little bit hard to see. Y equals 0. Okay, there is a y-intercept at 0, 1. So I know the graph is crossing through right here. That is really helpful, actually. There is an x-intercept at -2, 0. Oh, that is also really helpful. And remember, it can cross the horizontal asymptote, so that makes sense. That means I know this curve already on this side is just slightly going across that and hugging, because that determines the end behavior, that horizontal asymptote. So I know about that curve. I, however, have no idea what's happening in here. No idea what's happening in here. So we are definitely going to have to find at least 2 additional points. I'm going to say we better do like 1.5. And that will show me if I have like a curve in here, a curve in here. Now it is possible that I could be going up and down that way. I guess we could do maybe 1.5 and like 1.25 just to kind of get a really good feel for exactly what's happening in there. So I'm doing 1 1/4 and 1 1/2. And I definitely need to do something past the 2, but 1 point will be sufficient. If I do f of 3, I'll be able to tell if I have like a curve like that or a curve like that. All right, so let's find those 3 points and move on from there. I can plug them in either spot. I'm going to go ahead and plug them in my calculator so you can have the practice as well in your calculator. All right, so let's see. The function itself is x plus 2 in parentheses over x squared minus 3x plus 2 in parentheses. So that's the function itself. I want to evaluate it at 1.5. So I'm going to take my 1.5 and store it as my x, plug it into my original function, and that gives me negative 14. Wow. Okay. Then I'm going to try 1.25. I'm going to go ahead and store that as my x. And let's plug that into that original function again. And that gives me negative 17.3 repeating. Wow. At least they're both negative. So I know I'm down. It's down under the x-axis. Let's try 3. Let's do 3 store x and plug it into that original function. You can do this by hand if you'd rather, and that's at 2.5. All right, let's put in those points and see how it looks. So at 1.5, I'm at negative 14. So I'm here and 1, 2, 3, 4, 5, 6, all the way down here. I'm just gonna go down low here. At 1.25, I was at negative 17, so I'm even a little lower. That tells me I'm going like this. If for some reason you were wondering, could the graph possibly curve back up? Technically it could. You could do 1.75. You're gonna find it's balanced down here, but that would be a good check if you weren't sure. Let's also put in our other point, f of 3 is 2.5. 1, 2, 3, 1, 2.5. I'm up here, which means I must be curving something like this. And this is what my function is going to look like. Now, when I check this in my calculator, I'm going to type in the whole equation with a parenthesis on the top and the bottom. So I want to make sure on the top I put my x plus 2. And on the bottom I put my x squared minus 3x plus 2. Close that. And let's take a look. Does our graph look like that? We're not going to be able to see down here. If I were to zoom out, hopefully it will pick it up. I'd really have to change my window, but it would confirm, yep, you can see it there. It's here, here, and here. Good check, but you can see how you really need to do the work by hand to get all this important information. Now, that's our first example. We are going to work for 3 more, but I'm going to move this to a different video link. So you can click on the second video link to view our final 3 examples. So I will meet you at the next video. See you in a few minutes.